theorem 2 was that equal chords of a circle subtend equal angles at the center, right? Now, this theorem 3 is the converse of theorem 2. Okay. Theorem 2 was that if there are two chords in a circle having equal length, then they will subtend equal angle at the center. And converse of this theorem 2, which is theorem 3, it says that if the angles subtended by the two chords at the center of a circle are equal, then the chords are equal. Okay, then the chords are equal. Okay, so what it says that if there are two chords, right? As we have here in AB, in this figure, AB and CD. AB and CD are two chords and they are subtending equal angle. If this is theta, then this is also theta. If they are subtending equal angle at the center of the circle O, right, then the length of the chords will also be equal. That means AB will be equal to CD in length, right? So this is theorem 3, which is the converse of theorem 2, right? So let's see how to prove this theorem. Okay, so let's see how to prove this. Now, what is given here? Given is that there is a circle, as you can see here. This is a circle, suppose C, with center O and the radius is R. Okay, so given a circle that is C with center O and the radius R, in which AB and CD are two chords. These are the two chords such that these are the two chords such that angle AOB is equal to angle COD. This is already given, right? This angle AOB is equal to angle COD within this figure, right? These are the angles subtended by the chord AB and CD respectively, right? So this is given here. And what we have to prove? We have to prove that the two chords are equal in length. That means AB is equal to CD. AB and CD are the two chords subtending equal angle. So now we have to prove that these chords are equal in length, right? So now let's see the proof of this theorem. Now, if you can see this diagram, we have two triangles here. Triangle AOB, this is a triangle, and triangle COD. These are the two triangles within the circle, right? By these chords and the radii. Now, in these two triangles, if we prove that these two triangles are congruent to each other, then we can easily prove that AB is equal to CD by CPCT, right? So we are going to do same thing here. We will prove that these two triangles are congruent. So write down in triangle AOB and triangle COD, right? What we have here, OA is equal to OC, isn't it? OA, this length, will be equal to OC, this length. Why? Because both are the radius of the circle, right? Okay, so both are radius of the circle. Write down each equal to the radii, each equal to R, that is radius. Okay, now OB is equal to OD, right? Similarly, OB and OD both are the radius of the circle. This is also R, this is also R, right? So both are equal to R, each equal to R. Okay, and angle AOB is equal to angle COD. Why? This is already given in the question, given in the theorem, right? That they are subtending equal angles, right? So this is given here. Angle AOB and angle COD are equal, right? That means what? Triangle AOB is congruent to triangle COD. By which criteria? By which criteria? Side, angle, side. SAS, right? Okay. So by the criteria SAS, we have proved that these two triangles are congruent to each other, right? By SAS congruence criteria. Is that clear? Okay. Since these two triangles are congruent, right? Hence, we can say that AB is equal to CD by CPCT, means corresponding parts of congruent triangles. So once we have proved that the two triangles are equal to each other, means congruent to each other, then all the corresponding parts will also be equal. That means AB will also be equal to CD. So in this way, we have proved that if the two chords are subtending equal angle at the center of the circle, then these chords will be equal in length. So we have proved this here, the theorem 3. Okay, so I hope everybody understood like how to do this. Yes or no? Now look at the next theorem, theorem 4. It says that if two arcs of a circle are congruent, then the corresponding chords are equal. What does it mean? That if suppose we have a circle, as you can see here in this figure, there are two arcs, right? Arc AB from here to here and arc CD here to here, right? So these are the two arcs. And if these two arcs of the circle are congruent, means they are equal, they are same, they are equal in length, right? Then their corresponding chords, their corresponding chord will be chord AB is the corresponding chord of arc AB and CD is the corresponding chord of arc CD. Then these corresponding chords of AB and CD will also be equal in length, right? So this is theorem 4 related to chord properties. Is that clear? Okay, so in this theorem, what is given to you? It is given that the two arcs are equal, right? Okay, so write down what is given here. Given a circle, suppose this is a circle C, O, comma R, right? Circle C, O, comma R, in which arc AB, this is the symbol of arc, is congruent to arc CD, right? So arc AB and CD are congruent, right? Now, what we have to prove? To prove that chord AB is equal to chord CD, means this AB length, chord AB in length is equal to chord CD in length. Is that clear? This we have to prove here. Okay. Now, how to do this? Proof. Okay. Now, suppose, let's assume that AB and CD are the two chords, right? Are the two arcs. AB and CD are two minor arcs. Okay. Because the arcs may be minor, maybe major, right? So suppose it is, these are the minor arc, right? Now, what we will do? We will join, we will do a construction here, right? We will join OA, OB, similarly OC and OD, right? So we will join all these points, right, with center O. Okay, now, so write down join OA, OB, OC and OD, right? Now look at these two triangles. In triangle AOB and triangle COD, right? Again, in these two triangles, what we have? OA is equal to OC. OA is equal to OC because both are the radius, each equal to radius. Is that clear? Okay. So OA and OC both are radius. Similarly, OB and OD both are radius. So OB and OD are also equal, each equal to radius of the circle. Okay. And angle AOB is equal to angle COD. Angle AOB is equal to angle COD since they are congruent, right? Why? Why they are equal? Because when the two arcs are congruent, right, then they subtend equal angle at the center. Is that clear? Okay, so you can write down since arc AB is congruent to arc CD, right? They subtend equal angle at the center. AOB will be equal to angle COD, right? Now, from this, we can say that triangle AOB is congruent to triangle COD. By which criteria? By SAS. Congruence criteria again. Okay. Right. So triangle AOB and triangle COD are congruent to each other by SAS property. Right. Side, angle, side. Right. By side, angle, side congruence criteria, we have proved that triangle AOB is congruent to triangle COD. Right? Now, since these are congruent triangles, hence AB is equal to CD by CPCT, corresponding parts of congruent triangle. So since we have proved that these triangles are congruent, the corresponding parts, other corresponding parts will also be equal. That means AB and CD will also be equal. So in this way, we have proved that if there are two arcs which are congruent within the circle, then the corresponding chords will also be equal in length, right? So this is the case when AB and CD are assumed that these are the minor arcs, right? We can assume other case also that AB and CD are the major arcs. In that case, BA and DC will be the minor arcs, and you can prove the same thing for those arcs. And in that case, in both the cases, you will get AB is equal to CD, right? Okay, so that is exactly similar. So if these are the major arc, in that case, the other part of the circle means BA and DC will be the major arc, and you can prove the same thing, will be the minor arc, and you can prove the same thing for that, right? And in this way, you can easily prove that AB and CD are the two equal chords. Is that clear? So we have done this theorem, theorem 4, right? We have proved this theorem, which says that if the two arcs of a circle are congruent, then the corresponding chords will also be equal. Now, look at the next theorem, theorem number 5. And this theorem is the converse of the previous theorem, theorem 4. Okay. And what it says that if two chords of a circle, are equal, then their corresponding arcs are congruent, right? In the previous theorem, theorem 4 was, it was that if the two arcs are congruent, then the corresponding chords are equal. Now, in this theorem, what we have, if the two chords of a circle are equal, then their corresponding arcs will be congruent, right? Now, these congruent arc may be the semicircular arc, or the minor arc, or the major arc, right? So this is theorem number 5, which we are going to prove now. Okay. So very first, we will write down what is given here, right? What is given and what we have to prove, right? So write down. So given here is a circle. Suppose we have a circle here. This is a circle. In which we have two arcs. The center is O. Okay. So this is a circle C, O, comma R. Radius is R and center is O. So write down a circle is given. A circle O, comma R. Okay. In which, what is given? In which, given that chord AB is equal to chord CD. I have not drawn the chord yet. Because we are going to discuss different cases. Accordingly, I will draw. Now, chord AB and chord CD are equal in length. This is already given here. And we have to prove here that arc AB, the corresponding arc AB of the chord AB and the corresponding arc CD of the chord CD are congruent, right? Okay. Where AB and CD are either semicircular arc, okay, either they are semicircular arc, minor arcs, or major arcs, right? So whatever be the case, right, these corresponding arcs will be same, will be congruent. This we have to prove, right? Now, how to prove this? To prove, we will first assume the cases here, right? Okay. So let's take the case 1. And the case 1 is that suppose AB and CD are diameters, right? Because only diameters divide the circle into two equal half, right? So suppose AB and CD are the diameters, because diameter is also a chord, right? So now let me draw the two chord here. So suppose this is here AB, okay, and this is CD. AB and CD, right? And these chords are passing through the center of the circle, and that's why these are the diameters, right? So what is the case 1? When these arcs are the semicircular arcs, means AB and CD chord are the diameter of the circle, right? So this is the first case. Now, in this case, AB and CD, AB and CD are semicircles. These arcs are the semicircles, yes or no? Right? So if you can see here, this one, this AB, this CD, right? So what are these? These are the semicircle, right? So AB arc and CD arc are semicircles, right? With the same radii. With same radius means with the same radii, right? Means that means what? Since their radii are same, so can we say that arc AB is congruent to arc CD? Yes or no? Right? Since they are having same radii, right? Radii are same. This is equal to this, and this is equal to this, and all are the radii. That means, what does it mean? The arc are congruent, right? That means what? AB is equal to CD. Getting it? That means AB, the semicircular arc, congruent to CD, right? What does it mean? It means that if these are the two semicircles, right? Means these are the two semicircular arc with the same radii, then both chords will be equal because both are the diameters, right? Is that clear? And semicircular arcs are having the same radii, right? Diameter is the twice of the radius, right? Means that means AB and CD are equal. Is that clear? Right? So this is the case one, right? Now look at the case two. Case two. Case two, when chord AB equal to chord CD, right? Where AB arc and CD arc are minor. These are minor arcs. Okay. So we have assumed here this time case two that these are the minor arcs, right? Now if these are the minor arcs, now what we will do? Now let's again draw a circle here, right? Center is O. Okay. Now draw the two chords here, AB and CD. This is suppose AB. This is CD. Okay. AB and CD. Okay. Now we will join the ends of AB and CD with O. Okay. So join OA, OB, OC, and OD. We have joined them. Okay. So right now, join OA, OB, OC, and OD. Right now, since we have joined these, we can see here the two triangles AOB and COD. Again, we will do the same thing here. In triangle AOB and triangle COD, what we have? AB is equal to CD, right? It is already given that the two chords are equal in length. This is given in the theorem itself, right? So AB is equal to CD, it is given. OA is equals to OC, each equal to radius, right? Each equal to R. And OB is equal to OD, each equal to R. All are radius here in this circle, right? So OA is equal to OC, OB is equal to OD, right? And all are equal to radius. And AB is equal to CD. This is already given in the question that these are the two equal chords, right? So now, can we say that triangle AOB is congruent to triangle COD? Yes or no? By which criteria? By SSS congruence criteria, right? Side, side, side. This is equal to this is equal to this, and this line is equal to this line, right? AB is equal to CD. So all the three sides, all the three corresponding sides are equal. Therefore, we can say that triangle AOB is congruent to triangle COD by SSS congruence criteria. Is that clear? Okay. Now, since we have proved that these two triangles are congruent, so can we say that angle AOB is equal to angle COD? Right? AOB will be equal to angle COD. This angle is equal to this angle by CPCT, corresponding parts of congruent triangle. Right? Now, since angle AOB and angle COD are equal, right? What does it mean? That means measurement of AB, chord arc AB will be equal to measurement of arc CD because angles are equal, right? Therefore, the corresponding arcs will also be equal in measurement, right? So in this way, we have proved that AB, arc AB is congruent to arc CD. Is that clear? So here we have proved. So first we have proved that these angles are equal. Since angles are equal, right, the arcs, measurement of the arcs will also be equal, right? That means these two arcs are congruent to each other, right? So in this way, the case 2, where AB and CD are the minor arcs, we have proved that these are also equal, right? So if the chord AB and chord CD are equal, then their corresponding minor arcs will also be equal. Now this was case 2, when arc AB and CD are the minor arcs. Now, case 3. And case 3 is that chord AB is equal to chord CD, right? But the corresponding arcs AB and CD are major arcs. Okay, so these are the major arcs of the circle, right? So in this case, how we will prove that the arcs are congruent, right? So if arc AB and CD are major arc, now look at this figure again. If AB and CD are the major arc, right? So this is AB, major arc, and this is CD, the major arc, right? If these are the major arc, in that case, the other part of the circle means this one, BA, this one, this will be the minor arc. If AB is the major arc, then BA will be the minor arc. Similarly, if CD is the major arc, right? If CD is the major arc, this one, then DC will be the minor arc from here to here, right? Is that clear? So, so we have assumed here that AB and CD are the major arc. That means, in this case, BA and DC are minor arc. These will become the minor arc. Everybody getting this, right? Now, AB is equal to CD, right? AB is equal to CD, right? That means, can we say that BA is equal to DC? If AB is equal to CD, then can we say that BA is equal to DC? Both are the length of the chord. That means BA arc will be congruent to DC arc. If the chords are equal, it is already given here in the question, then the arcs will be congruent, right? But these are the major arcs, right? That means measurement of BA, arc BA is equal to measurement of arc DC, right? So when we are saying congruence, that means we are talking about the measurement, right? That means if we subtract both of them with 360 degree, 360 minus measurement of BA, measurement of AB, right? That will be your BA, isn't it? So can we write it like this? 360 minus measurement of AB arc, right? Measurement of AB arc means, or BA arc, means we are talking about the angle which this arc is subtending, right? So this is 360 minus measurement of DC arc. Hearing it? That means what you will get if you are subtracting AB arc from 360, that is measurement of, means both the sides you can remove this 360, that means AB arc, measurement of AB arc will be equal to measurement of CD arc. Getting that? Okay, and from here you can say that arc, the major arc AB is congruent to major arc CD. Is it clear? Yes or no? Please correct this. This is BA, right? Okay. So in this way, we have proved that both the arcs are congruent, right? When these are major arcs, even then they will be congruent to each other, right? Congruent to each other if the corresponding chords are equal, right? So in all the cases, we have proved that. Therefore, in all cases, AB, if AB is equal to CD, that means corresponding arc AB, corresponding arc of the chord AB will be congruent to the corresponding arc of CD, the chord CD, right? So if two chords in a circle are equal in length, then their corresponding chords will also be congruent. Is that clear? Everybody understood about this? So this is your theorem number 5.